In part 2 of the lecture, I will discuss the two systems that I used as examples for vibrations, namely a mass attached to a spring and also pendulum. I will talk about the restoring force that is responsible for the oscillations, as well as the effects of inertia, and I will also define the period of oscillations based on the physical parameters of each system. Let's first discuss oscillating mass on a spring. The oscillations of a mass attached to a spring are a result of the inertia of the mass and the restoring force, which is elastic force in this case, which arises due to the nature of the spring and how it functions. Let's first look at the effects of inertia on the oscillations. So here is my system, a spring and a mass or a bob with mass m attached to it. So if I put the bob below the equilibrium position and let go of it, the spring, because it's stretched, will pull it back up. So a force arises here in the spring because it's stretched beyond its equilibrium position. And so this force pulls this bob up. However, when the bob reaches the equilibrium position here, it doesn't stop. And that is because it has some mass, which means it has inertia. Newton's first law states that when an object is in motion and there is no external net force acting on it, the object will continue to move the way it was moving before. When this mass is right at the equilibrium position, the spring is neither stretched nor compressed, which means that there is no force that acts on the bob right when it's at the equilibrium position. So then the bob passes the equilibrium position and starts to compress the spring. Now, a force arises in the spring that wants to stretch the spring back to the equilibrium state. And so this force is going to slow down the bob until the bob stops somewhere here, and then the force pushes it back down, and then the bob reaches equilibrium, but it doesn't stop there because right at equilibrium there is actually no net force acting on it. Only inertia makes it pass the equilibrium point, and then the bob reaches this lowest point. Now the spring is stretched again, so a force arises that pulls the bob up. So the bob starts to go up, passes equilibrium, reaches the top, and then goes back down, and then back up. And so up and down, up and down, up and down. And it never stops here at the equilibrium position because of its inertia. Now let's look at the restoring force that acts on the bob. So when the bob is below the equilibrium position and it's released, since the spring is stretched, a force arises in the spring that pulls the bob up. So I said that this is the restoring force, but in its nature, this is elastic force. So this is the elastic force of the spring. The elastic force pulls the bob up until it reaches a point somewhere here where it stops. But why does it stop? It stops because once the bob passes the equilibrium position, now the spring is being compressed, and so the elastic force changes direction. Now it's pushing down. So that slows the bob down until it stops. And then this elastic force pushes the bob down. Once the bob passes the equilibrium, the spring starts to get stretched. Elastic force arises in the spring, but now it's pointing up. So as the bob is coming down, the elastic force is pushing up. So that slows the bob down until it stops right here. And then it starts to go up. And so up and down because of that elastic force. So right when the bob is at the equilibrium position here, the spring is neither stretched nor compressed, then there is no elastic force acting on the bob. So when the bob is at this level, no force acts on the bob. That's why the bob, at this moment, the inertia plays role for the oscillations. The bob doesn't stop here, it passes because of inertia. Now let's see how the period of oscillations of a mass hanging from a spring is determined by the physical parameters of that system. What are the physical parameters of the system? Well, we have the mass of the bob and then we have the spring itself. And we know that there's various types of springs. There are stiff springs and then there are soft springs. And we know that stiff springs are not going to be able to be stretched too much or compressed too much because they're stiff. So that means that they are not going to be oscillating for too long once stretched or compressed. And then we also know that soft springs are easier to stretch or compress, and then those springs will oscillate for longer periods of time because they're soft. So the softness or the stiffness of the spring is determined by an internal or intrinsic parameter of the spring. So the period of oscillations of a spring depends on the stiffness of the spring, and the intrinsic parameter that determines the stiffness is called a spring constant, and we label that with capital K. The spring constant is related to the stiffness of the spring. A larger spring constant means stiffer spring. Smaller spring constant means softer spring. The units for the spring constant are newtons per meter. Then, the period of a mass hanging from a spring is calculated as 2 pi times the square root of the mass of the bob divided by the spring constant. So here, as you can see, the larger the mass for the same spring, meaning the spring constant is constant, the larger the period of oscillations. And then for a fixed mass, the larger the spring constant, which means a stiffer spring, the smaller the period of oscillations. Or, the smaller the spring constant, the larger the period of oscillations. Now, this formula here gives us a way to calculate the period of oscillations of a mass hanging on a spring by purely using the physical parameters of the system, meaning mass and spring constant. Once the period is calculated using that formula, then one could calculate the frequency of oscillations using the relationship between the period and the frequency. Let's do one example of the application of the formula for the period of a mass on a spring. Calculate the period of a mass on a spring for a mass of 0.5 kilograms and a spring with a spring constant of 20 newtons per meter. So the formula for the period is 2 pi square root of m divided by k. And then I will substitute the values that I know from the statement of the problem. And that gives us 2 pi times square root of 0.5 kilograms divided by 20 newtons per meter. Let's do the units to show you how you get the units of the period to be seconds. So we have square root of 0.5 kilograms divided by 20 newton. 1 newton is 1 kilogram times meter per second squared. And then we have divided by a meter, so this is the same as multiplying by the inverse meter. So kilograms cancel out, meters cancel out, and the second squared will flip on top here in the numerator. And so this becomes 2 pi times square root of 0.5 seconds squared divided by 20, which is 0.99 seconds, or approximately 1 second. Now, if I wanted to find also the frequency of oscillations, I simply need to take the inverse of the period, or that is 1 divided by 1 second, which is equal to 1 hertz. Now let's look at a pendulum and define the restoring force for that system, and then I will talk about the period of a pendulum. So first, let's talk about the role of inertia in the oscillations of a pendulum. Here is my pendulum. We have a string with length L and then a bob with mass M attached to it. So if I pull the bob to this position from its equilibrium position and let go, we know that the bob is going to start to move towards equilibrium. It's going to pass it. It's going to swing on the other side. It will stop right here. Then it's going to swing back. It reaches this initial position and then go back again. So back and forth, it's oscillating. But why is the bob not stopping here at equilibrium position? Well, it's simply because when the restoring force pulls on the bob, it moves it towards equilibrium. When the bob is at equilibrium, there is no restoring force at that position. And so the inertia of the bob makes it continue go, since there is no net force acting on the bob. Once the bob passes equilibrium, the restoring force reverses direction, and starts to pull on the bob. So the bob slows down, it stops right here. Then the restoring force makes it go towards the equilibrium position. And so it passes it because of its inertia, and it reaches the other side. And so back and forth because of the restoring force, but it doesn't stop right here at the equilibrium position because of inertia. Now let's look at the restoring force itself and see where it comes from. So here is my pendulum, and I pulled the bob to this initial position, and then when I let go, the bob is under the action of two forces. We have tension in the string and then the weight of the bob due to the gravity of Earth. And so then the net force is the resultant force of those two forces acting at the same time on the bob. And so the net force is directed somewhere here. And so as a result, the bob is going to swing like this, along this trajectory. And when it reaches the equilibrium position, this net force vanishes because the tension will be pointing straight up, the weight will be pointing straight down, they will be balanced, so there will be zero net force acting on the bob when the bob is right here. And so the bob continues to move because of its inertia, and once it gets on the other side of the equilibrium position, then the restoring force appears again. Now the tension in the string, of course, points like so, the weight like so, and so the restoring force or the net force now points in that direction. So once the bob passes equilibrium and starts to climb up, the restoring force is pulling it down, so it slows down, it stops. And then because of this restoring force, the bob starts to go towards equilibrium again. Right at the equilibrium position, there is no net force acting on the bob, and because of its inertia, it passes equilibrium, swings to the other side, gets here. Now, once it passes equilibrium, the restoring force appears again. Now it's opposite to the direction of motion. That slows down the bob until the bob reaches the highest point. Then the restoring force pulls it back down towards the equilibrium. Passes equilibrium, the restoring force appears again. It's pulling on the bob, so it slows it down until it stops. And so back and forth under the action of this restoring force, which only appears when the bob is either to the left or to the right of the equilibrium position. Now, what parameters are used to calculate the period of oscillations of a pendulum? Well, the obvious candidates will be the length of the string and also the mass of the bob. Well, it turns out that the mass of the bob actually doesn't affect the period of oscillations. The parameter that affects the period of oscillations is the length of the string and also the gravitational acceleration. And so the period of oscillations of a pendulum is calculated as 2 pi times the square root of the length of the pendulum divided by the gravitational acceleration. Here you can see that as the length increases, that will increase the period of oscillations, or as the length of the pendulum decreases, that will decrease the period of oscillations. You also see that for the same length, the period will change depending on the gravitational acceleration. So that means that a pendulum on Earth will have different period compared to that same pendulum on the Moon. And that is because the gravitational acceleration is different. Let's do one example problem using the definition of period of a pendulum. Let's calculate the period of a 2-meter long pendulum. So the length of the pendulum is 2 meters, and the period is calculated as 2 pi times square root of L divided by G. So that is 2 pi times square root of 2 meters divided by 9.8 meters per second squared, which gives us a period of 2.8 seconds. If I wanted to also calculate the frequency of oscillations, the frequency is equal to 1 divided by the period, so this is 1 divided by 2.8 seconds, or this is 0.6 Hertz.